Hey Data Junkies, welcome back. I love you all. You guys are so important to me. And I love what I'm doing here with stats, so this is really like a best life scenario. So, sorry, I just had to get that out. Anyway, we're talking about simple linear regression. We are well underway. We just got done talking about how to use categorical variables. I introduced the concepts of how to use binary variables as your independent variables. You can't use them as your dependent. That takes us outside of linear regression. Asterisk. I'll come back to that later if we get the chance of the bonus videos at the end of the term. But here I just want to take a moment and give you some additional categorical examples on how we're dealing with these sorts of independent variables here. So let's just go ahead and just do another brief example walkthrough here. So we're going to return to the Starbucks data because it's just fantastic. And we're going to ask the question, is an espresso a good predictor of caffeine relative to other Starbucks coffees and teas? So we're starting with the Starbucks data. I've already got it into the data set here. It's called Starbucks. And I'm looking specifically at two variables. I'm looking at beverage category and caffeine as it is in milligrams. And when I run a structure on this, again, always check your variables. Just don't go directly diving into regression. You're going to run into all sorts of issues. So beverage category and caffeine are both factors. I would have expected that with beverage category since these are going to be groups of drinks. But caffeine, in milligrams, that should be a number, so I may have to take a closer look at this. So let's just do a quick setup for our variables here to make sure we're on the right track. Looking at beverage category, I have 9 different types of beverage categories. Identified that with the levels function. And so I'm going to go ahead and do a recode out of the car library. I'm turning beverage category into a number so I can quickly move through the recoding process. And I'm turning those that identified as espresso, which would be the classic espresso drink and the signature espresso drinks. Those both had espresso in the name, so I'm coding those both as 1, and all of the other drinks are being coded as 0, or a non-espresso drink. I then do a bivariate table to kind of double check my recoding, and indeed, classic espresso and signature espresso drinks were both coded as 1, the others are coded at 0, so good job us. Then let's go ahead and take a look at that caffeine variable. I'm running a levels on that to see, since it was a factor, what do the levels look like? And you may remember this particular one. This was the variable I gave us way earlier in the course, back in our descriptive days, and said, you need to learn how to fix an ugly variable that's not coded the way you think it might be. So we're going to repeat this particular look here. And so caffeine, when I look at the levels, there's a couple problems going on. First of all, the numbers are being stored as text, so it is putting them in sort of a numerically alphabetical order, if you want to think of it that way. So the numbers themselves are out of order. And then also, the very first one is a blank value, and we've got 2 options for varies, one with a lowercase v and one with an uppercase v. So we have some data entry errors that we need to get rid of. So to fix that, I'm just going to briefly store this into a new variable so I don't overwrite my other one. I'm calling it caf.mg. And inside those, I'm turning the blanks and the varies options into missing. Once I have those, I'm doing a drop levels on it because it's a function. I don't want those levels tagging along. And then I go ahead and just do my as character nested inside as numeric to translate all of those numbers stored as text into actual number values that they represent. And from there, I now have a numerical variable that's ready to go, with caffeine being anywhere from no caffeine up to 410 milligrams of caffeine, with an average of about 89-90 milligrams of caffeine. Then I'm going to go ahead and just do my correlation on there. Again, correlations aren't necessary. I just like to see the relationship up front. And I see that it is strongly statistically significant with a p-value of 0.007, and a correlation value of 0.018 rounded. So it's a small correlation, but it is positive. So as we have, as we go to because this is a binary, we say as we go to an espresso drink, we tend to have more caffeine than if we're not an espresso drink. We can't think of it in terms of like as we continue to become more espresso, because it's only a binary choice. You are or are not. So let's go ahead and flip this into the regression here. I'm regressing the amount of caffeine in milligrams on being an espresso drink or not. It is highly statistically significant, as we saw with the correlation. The coefficient for being an espresso is 23.3 rounded. So we can take that to say that an espresso drink compared to non-espresso drinks would have an expected increase of 23.3 milligrams of caffeine. Let me put that differently. An espresso drink corresponds with an increase of 23.3 milligrams of caffeine compared to non-espresso Starbucks drinks. Remember, these are Starbucks drinks. All right, and if we were saying that zero value, because zero values are non-espressos, So non-espresso drinks would fit with our intercept, which happens to be about 79 rounded. So non-espresso drinks will have an average 79 milligrams of caffeine. And see how that works out nicely with our y-intercept when we have a 0-1 dichotomy? It's beautiful. Much easier than when you have it 0-1 or other sorts of numeric coding. And if we just want to look at our multiple r squared, it's a very small multiple r squared. Well, small in terms of the numbers, but it's still meaningful that being an espresso drink or not corresponds with explaining about 3.2% of the variation. 3.2% can still be meaningful given that when you're talking about all the different reasons of why something is what it is, this is still a nice size number. Let's go ahead and do one more example here for you. I'm turning to our friend the General Social Survey, and there's a series of questions in there where they ask people on 11 or 12, it was 11 different questions, if they had an understanding about a specific scientific knowledge, such as, is the middle of the earth, the core, is it hot? And they would get it right or they would get it wrong. And so what I did is I'm looking at all of these here, and I'm comparing these by their political views. So I'm going to add up all of the scientific knowledge to see how much scientific knowledge somebody has and see if your political views have any sway on how much science you might happen to know. So on the screen here, I've got a nice long mess of code. This is all of the recoding I did. So these are the original variables out of the GSS that I'm looking at. Things like, is the middle of the earth warm? Is radioactive decay natural? Does the male, the father, determine the gender of their child to be male or female? These sorts of questions. And I happen to know the answers from them, so I coded them out as being correct or incorrect. So 1 would indicate it's correct, 0 would indicate that it's not correct. Then I'm going to go ahead and combine them all. I check each one to make sure they coded properly. Then I combine them all into a scale, and I get this numerical scale that's going to become my dependent variable, and somebody's going to have an answer between 4 correct answers and 11 correct answers. So 11 mean they got them all right, and nobody got them all wrong. The lowest score someone got out of 11 questions was 4 of them correct, and so that's our range that we're working with here. And now I'm going to go ahead and take a look at my dependent variable. I'm going to use the political values here. So here I'm looking at a 7-point ordinal scale to go from extremely liberal to extremely conservative. And 1 would be my level function of how liberal they are compared to how conservative they are, being 7 high. So as my ranks get higher, I am more conservative. Let's go ahead and see what this looks like when I do my correlation. It is a very small p-value, 0.002 rounded, and it has a small to moderate, closing in a moderate correlation here, and it's negative. So that's saying that as my ranks of political values increase, I tend to have a lower scientific knowledge score. Again, it's in that moderate scale, so it's not an extremely strong correlation. Let's go ahead and look at this in terms of the regression output. In our regression output, we are also strongly statistically significant, carrying over from the correlation test. And our coefficient for the political views is negative 0.3445. I'm going to round this as negative 0.3 for the interpretation. So that's saying for each additional rank increase in your political views, so for each additional rank as I become more towards extremely conservative, I have an average corresponding rank decrease in correct answers of scientific knowledge. So a 1 rank change, as I go from being conservative to very conservative, or liberal to in the middle. So as I go a 1 rank change in my political views, I'm only moving a third, say about a third of a point on my scientific knowledge, which is not very meaningful at all. I need to get at least a 0.1 to have any sort of meaningful impact. So let's see how many rank changes I would need. Well, if I have about a third of a difference in my coefficient, I need about a 3 rank change. So if I move 3 ranks, that's effectively going from being extremely liberal to being neutral. Or if I go from neutral to being extremely conservative, that's going to get me a 1 point change on my scientific knowledge. So although I'm strongly statistically significant, I'm going to call this one a bunk when it comes to substance, right? The meaningful differences. Having to go almost halfway across my political spectrum change just to get 1 more right or less answer on scientific knowledge isn't very meaningful. So although statistically significant, I would say that political views is not very relevant for determining explanation. Even though my R squared is telling me that I'm explaining about 7.5% of the variation, while 7.5% of the variation is being explained, it's not a very meaningful impact when we're talking about real-world differences here. right? Knowing one more thing out of 11 questions, it's about a 10% difference. You know, I'd have to leave that to the pundits to really figure out if 1 out of 11 is going to be meaningful. I say no. But that's going to go ahead and wrap up our extra examples here on dealing with some of these categorical variables. I'll see you all in our next video.